Good morning. Welcome back again to Geology 100. We're going to be continuing with another topic today that I kind of find rather interesting. The topic is geologic time. And one of the things about geologic time that I like is just the way in which geologists figure out what's going on with the rock layers in the earth. And so we're going to cover some of these issues today in terms of how geologists unravel things to come up with these numbers and ages of when rocks formations developed, when mountains built, and stuff like that. Okay? Now it's kind of a unique shot up here. I like to use these trilobites, a really kind of cool fossil, to begin our discussion on geologic time. And so I want to kind of introduce this in two ways. Geologists kind of work with time in two ways. Now, for a long time, we weren't geologists, we were just scientists. They were naturalists out there. They were lawyers and doctors and ministers and so on who were looking at fossils, basically. Looking at rock layers, they'd find these fossils, they wanted to know what they were. So for several hundreds of years, all we talked about is, well, this appears to be older than that. So it was really a relative statement about time. So we had this concept of relative dating. And once we get going, the first thing we'll do is talk about the relative dating principles and concepts today before we can talk about, well, how old is it in terms of years? So I can, honestly say in a relative dating time, I'm older than anybody in this room. Why? Well, I look older. You start to get wrinkled, you get shorter, and you get gray hair and stuff like that, right? It's a relative statement. But how many actual years am I older in terms of numbers? And so that's a different story, and that's absolute dating. So I could say, well, I'm 59. I'm going to be 60 this fall. So that's a numerical numbers thing kind of stuff. So how do geologists do that with rocks? Where do we come up with these numbers? So we're going to then focus on the absolute dating concepts and then wrap it up and talk about some things we do in terms of applied geology on this. I like throwing this little diagram in. And in the classroom, it's easy to look at and see here with a big screen. I know in distance in the future, when you're looking at this on a DVD, that the scale on the left is going to be hard to really read maybe. What this chart is about is, like how long does it take for a certain event to take place or a process? How long does it take to get a foot of sandstone, a foot of limestone? Or how long does it take for a radioactive element to break down and decay into something else, a stable byproduct? And so it's kind of an interesting chart in terms of things that take a long time to occur and develop versus things that are very, very quick. At the bottom end, we talk about the nuclear processes for nuclear reactions to take place. They're extremely fast. And this scale is a kind of a 10 to the minus 12th. It's scientific notation. In terms of, this is in years, so 10 to the minus 12th years is a very small amount of time. As we work our way up the chart, we can get into segments on earthquake waves. How long does it take for a shock wave from an earthquake to go through the earth itself and be picked up by our seismograms? So you're not going to be responsible for any numbers or anything on that. But, it's kind of a unique kind of diagram to understand time and processes. What's the lifespan of a human? It's gotten longer in terms of health care and people taking care of themselves and so on. And probably some genetic stuff thrown in as we evolve. I start with this diagram, and I'll come back to it several times. One of the things geologists, particularly historical geologists, like to say about things that they've provided to society, provided to an understanding of the earth, is this thing here, geologic time scale. An idea of coming up with a calendar. This is the geologist's calendar of when things took place, and we have these names up here, and it's just, again, it's a lot of interesting terms. You probably can recognize some in the middle, like Pennsylvanian and Mississippian, but most of them are different. And this is, how we applied a particular name to an age period, a time period. For example, geologists have to memorize this. We have to know all the subtleties, the breakdowns, the dates. We want to know when were the first plants, when were the first reptiles, when was the age of this, the age of that, when's the first fossil, how old are they? And this is how we communicate. I mean, today is what? Thursday, right? April what? 13th. Now you know that. You memorized them. You learned all those calendar times in grade school. Probably kindergarten or before that. But do you know where the words come from? Where does Thursday come from? Where does Tuesday come from? And Wednesday and Sunday? That's etymology, the origin of words. We'll talk a little bit about some of the origin of some of the words in this diagram, not Mississippian or Pennsylvania. I think that's going to be pretty obvious once we get to it. But this is kind of a contribution we have to understanding time, and we've got this vocabulary. This is our calendar. Now, not to bring up beer in terms of our vocabulary, this is a particular diagram I like to use to represent time in one way. And the most important part of this diagram that you look at today that you have to remember is what part of the Earth's time is represented by a particular era. It's called the Precambrian era. If we go back to this first diagram, in the bottom, over here on the left, you see the word Precambrian. And at the very bottom, you see 4600. That's really another representation in millions of years. That's 4.6 billion is what that's supposed to represent. We say the Earth is 4.6 billion years old based upon certain evidences that we've accumulated. And this whole segment, all the way up until when the green starts, is what's called the Precambrian era. Excuse me, it is. Precambrian era. They've broken it down into a different diagram. They call it an eon up on top for the green. I don't want you to get confused on that. But we've broken this thing into different subdivisions. The Proterozoic eon, the Archean eon, within that Precambrian era. But in this diagram, it only looks like it represents what? The bottom 1/5 of time. It's not. Precambrian represents most of geologic time. In fact, it represents 7/8. So remember that. I'll ask you that question. The Precambrian is one of the subdivisions of geologic time, and it represents 7/8 of all time for the Earth's history. Now, next two lectures we go into, when we get into the geologic history of the Earth, a little bit of this comes back, not so much the numbers, but what are some of the evidences in the fossil record and the rock record that tells us what's going on during the Precambrian. When did the first fossil come about? When did oxygen supplies change in the atmosphere? When did this happen? We'll get into that detail next time, okay? Now, as we work our way up in terms of relevance, like I say, the bottom 7/8 is Precambrian. It isn't until we get to the very upper part that we can start talking about other major events. From this little line right up here on top, the last 13% of time is really from the green upward. But why do we break these upper parts into smaller and more tiny divisions? Because we have lots of evidence in the rock record and the fossil record in this case. Lots of evidence. All right, so where do we work to start doing this analysis of time? Where did most of this come from? It came from paleontology. And paleontology, defined, is the study of ancient life. Paleo, the prefix paleo, means ancient. So paleontology is a study of life, ontos for life, analogy of study of something, so the study of ancient life. And this is based upon fossil plants and fossil animals that we've been able to find. So what's a fossil? Well, it's simply evidence of past life. That trilobite you saw in the very beginning opening slide is a fossil of a particular organism, an invertebrate, an arthropod. So here's where your biology comes into play. Now, in most cases, organisms, plants or animals, when they die, if their remains can get buried very quickly, And this tends to happen most often in sedimentary rock environments. Remember the chapter on depositional environments? Beaches, deltas, swamps, deep oceans, continental shelves, sand dune areas. If you can cover up the organism, the plant or the animal, and don't let scavengers get to it, whether they're birds or insects or bacteria, to break it down and destroy it, if you can bury it, it can become preserved. And there's lots of different preservation things that can happen to it. So I have this statement, fossils preserved in sedimentary rocks. What we use that for is to, one, figure out this relative age of fossils, and I'll bring those principles into play in just a bit. But it also tells us something about, if you find it in a certain rock type, we could say that that organism lived in this particular environment in the past. Is it a marine organism? Is it a terrestrial organism? Where do we find them today? So paleontology is really a blast. A lot of kids come into our program because they got all excited about dinosaurs usually when they're 3, 4 years old, and sometimes that passion stays with them. Paleontology jobs, there's not a lot of them. It's hard to get a job in paleontology. But some people stick it out because they love it. They really get involved in it. Yeah?
Do we have a major here at Fort Hays? Or you can,
yeah, you get a degree. Yeah, we have a degree emphasis in paleontology, yeah. We also have a master's program. We have one of the better master's programs in the mid-continent. So Dr. Zakshevsky, the curator of paleontology at Sternberg Museum, is one of the better teachers. Getting close to retiring, unfortunately, but hate to see him go. There's a collage of pictures up here, different things from our students, working up on the dinosaur dig. This is the dinosaur being prepared out in Salt Lake City. Dino Lab made this for us. Here's what, in the very bottom right-hand side, we had a fake fiberglass rock in there somebody put in. We didn't design it. Had a silver painted, pipe with a drill bit, and when it was kind of horizontal or directional drilling ideas, and that's supposed to be drilling in, find oil, and nobody liked it, especially in the department. We didn't design it, so I had gotten a wild hair years ago to change that out. We were involved in this dinosaur dig. I said, let's see if we can raise some money. We raised a lot of money to have this thing built, and so we finally had our actual dinosaur you see in Tamanic put over there. So I won't go into lots of detail about this. I usually had a complete whole lecture on the dinosaur display, but we kind of got rid of that this year. Kind of the logistics for distance learning situations. Sometimes these fossils are really just, besides being unique, have some value to them. We're always having people call us, bring samples in, send us pictures and email. What is this? Is this valuable? A lot of times now it's meteorite material, but these big coiled ammonite type things with the original mother of pearl, you go into rock shops, you pay a lot of money for this stuff. This is petrified wood, Petrified National Forest in Arizona here, and so some of this stuff has some value. I like this. It's just, these are fossil insects and plants. Our students collect this. I collected the one on the top left and the bottom right in this one spot we go to in western Colorado at Douglas Pass. And we dig around little rock layers, and they're neat to find. You can put them in a frame, put them on a wall. So there's a lot of art to it as well, but we learn a lot about the past with this. All right, so I think you can tell I've got some excitement about paleontology. That's what I was going to major in when I started college at Wisconsin, but I got diverted into archaeology for a year, and then I came back on the Group W bench and finished my geology degree, but ended up being a structural geologist. But I still have that passion for fossils and love to get into it. And so that's what these people were looking at in the past. And one of them was a guy named Steno. All right? And he created these principles that we use in relative dating. Now, what they worked mostly with were sedimentary rocks, sometimes volcanoclastic. Volcanoclastic simply means like ash that would fall down and bury things, that would create some really good fossil finds that we've got, like up in Nebraska. The ashfall beds are beautiful up there. So Nicholas Steno, you don't need to remember the date so much, but I want you to remember these principal names, especially names in red. First principle, principle of superposition. And I'll show you pictures of these in just a bit. Second one is called the principle of original horizontality. And the third one is the principle of lateral continuity. These are the principles they developed, especially Steno, got them into literature a long time ago. And they were applied in relative dating. That's older, that's younger, whatever it was. Okay? Now there are other principles that are more modern, and we'll get to those in just a bit. But I want to go through a series of little diagrams to kind of show you what some of these are. And they're fairly basic and pretty simple. Okay? Principle of superposition, original horizontality, and lateral continuity. Because I definitely have some questions about these on the test. Yeah, there's good old Steno. It seems like with those wigs, they all look the same in the past. All right, superposition. A little cartoon about superposition. I'm not that concerned you memorize this in a sequence of undisturbed layers, rocks. RX, by the way, means rocks. The important thing to remember is what's in red. I guess purple on the DVD that's going to end up. A little cartoon there, a little block diagram shows a bunch of layered rocks, like layered cake. Layer on the bottom was put down first. So what's the oldest? That's it. That's as simple as it is. Rocks on the bottom are the oldest. Rocks on the top are the youngest. It's like dust under your bed that builds up over the years, right? Okay? And so, unless for some reason, tectonic reason, it got turned upside down. How could you tell if a sedimentary rock layer was turned upside down? Remember the stratigraphic up principle things? Mud cracks, cross beds, and stuff like that we could use to figure out if a rock layer was upside down. That's why it says undisturbed. But for this class, I want you to remember the rocks on the bottom are the oldest. That's the principle of superposition. Now here's some real rocks, so we can just make the assumption, if this hasn't been turned over, that the layers down here are older than ones on top. That's it. Nothing difficult. Sounds fancy, but it's not. We look at our continental shelves where most sedimentary rock layers are deposited. They're nearly horizontal. There's a gentle slope of maybe 1 to 3 degrees till we get out to the continental edge. But in essence, rock layers of shale and sandstone and limestone are deposited nearly horizontally. And so we can often trace these layers for miles and miles and miles over great distances. And so we make that assumption that the rocks were initially deposited in a horizontal or nearly horizontal manner. If they're vertical, something's happened. Some event changed their position. So we start with this idea that they were deposited horizontally. And then we try to say, well, what happens to them after that? This little diagram's kind of trying to show the same thing, that deposited horizontally. Some of these aren't perfectly horizontal. However, over the bulk of the basin, that as we trace an individual layer, maybe we trace it 5 miles or 100 miles or 1,000 miles, but as we eventually get to the edge of that basin, they will thin out, but they have some kind of lateral continuity to them. If they're broken by a fault, or if they're vertical, or if they've been eroded off, or something's happened and you change that lateral continuity, well, that's an event. And we have to unravel what made that change. So these are pretty simple, basic ideas that Steno came up with. And then they get more complicated later on. All right, so mixed in with that, eventually through biological studies along with paleontologists, we came up with another kind of principle called the principle of faunal and floral succession. Now what that means is, and faunal is animals, floral is plants, okay, that as they looked at these rock layers and they say, hey, down here in the bottom, these oldest rock layers, there's no fossils in them. They moved their way up in the stratigraphic column and they started finding some fossils. Not a lot, very primitive, single-celled organisms. As they worked their way up, the types of fossils they found were evidences of very much more complex life forms, multicellular, and more of them. And then once in a while there'd be a big break and boom, everything was practically gone. A lot of things went into extinction. But it was still continually upward in the rock record from the bottom to the top, where we went from simple. So they succeeded. There was a succession of simple life forms to more and more and more complex life forms in that fossil record. And that's what they're kind of trying to show here. So if you ever go hike the Grand Canyon and you go down to the bottom and you're in these igneous and metamorphic rocks, once you get those sedimentary layers at that first platform called the Tonto Platform, and you work your way up to younger and younger rocks, you're not allowed to, by the way, collect fossils or hit them with hammers in a national park, but you would see that change take place from simple life forms to more complex life forms and more of them, with periodic bursts of extinction and then expansion again. So fossil organisms succeed one another in a very definite and determinable order over several hundreds of years of data collecting and looking at these in detailed drawings and age dating. This became a very useful tool to figure out where we were in the stratigraphic column. So this isn't something that's just, nil-nil type of thing. This is very definite, very exact, but it's relative. There are no numbers applied yet. Not any millions of years or thousands of years, nothing. It's just like, this is older and this is younger, as we went through that sequence. And it's not just in the Grand Canyon, it's on a worldwide basis on all of the continents. So once that became apparent, we were able to look at rock packages that we may not have studied and say, oh, I recognize this suite of fossils in these rocks. Oh, I saw them 15 miles on another canyon somewhere else. Gee, I wonder if I could correlate across that area. Sure, the rocks in between were eroded off, so we began to try to correlate over great distances from one road cut to a quarry or wherever to another one. And in doing so, you begin to create diagrams that were called structural cross-sections. And that gives us an idea that rocks were tilted and folded and bent between great distances by just picking up and using the fossils to do that correlation in the rock layers that they were in. All right, another principle that came into our vocabulary is this long, drawn-out word, uniformitarianism. Uniformitarianism. Now, James Hutton, who proposed this idea, came up with another way of expressing it in a more simple way, saying that the present is the key to the past. Now, what the heck does that mean? I mean, let's look at the word uniformitarianism. What other word that stands out that's in it? Uniform. And a lot of people looked at that saying, that means that everything is uniform forever. Well, that's misleading. That's not true. Not all mountain building takes the same amount of time. Not all volcanoes erupt at the same rate. Not all rock layers sediments pile up at the same rate. That's what people thought it meant. It's not. It's referring to the idea of looking at certain laws. Like if you mix two types of solutions in chemistry, the same thing's going to happen under the same pH, same temperature conditions, same pressure conditions. Whatever that may be, you can cause something to precipitate out an experiment, and you can do it over and over and over again. We could drop certain sediments in different kinds of fluids as if there's sediments dropping to the bottom. So what geologists do is go to all these places in the world, the glacial environments, the beaches, the deep sea, and we measure stuff. How long does it take for that to happen? That's kind of that original diagram with a little chart of time I showed you. Okay? And now we know that the law of gravitation hasn't changed, not to our knowledge yet. Everything still wants to drop at the same rate, same acceleration rate. So it's a very predictable things in chemistry, gas laws, and so on. Okay, so the natural laws don't change. That's what's uniform. Natural laws don't change. So in the word uniformitarianism, that's what they're talking about. However, rates and intensities, like Hawaii volcanoes, they're kind of bubbly and slow. Mount St. Helens, Mount Pinatubo, they're pretty, explosive and very quick. That's what changes. You go down to Padre Island, March, April, and it's kind of mellow. Back in the back barrier, there's hardly anything being deposited. It may take 20 years for something to change back there. But then a big hurricane comes along, and hurricane season blows a whole bunch of sand back there, rains a lot, more sand runs, flushes off the land, and you might get 2 inches of sand in 2 weeks, and 1 inch of mud in 30 years. So those are the things that vary. That's why we study that part. But remember that the concept of uniformitarianism means that the present, by studying now, is the key to the past. Because we make the assumption that gravity and chemical reactions were the same 4.6 billion years ago. All right, now some other types of concepts. Index fossils. If we're talking about time, Okay? If we want to index a very short amount of time, what was another little trick of the trade with relative age dating, okay, to narrow that gap down, at least within the rock record, to say this happened in a very short geologic time, as opposed to, well, maybe it was really long and we can't figure it out. Well, the idea of index fossils came into play. Now, what's an index fossil? Well, it indexes a small amount of time. Well, how can it do that? There's 3 criteria that have to be met for a fossil to do that. Number 1, it better be short-lived. If that species has lived for the span of the Earth's time, like some cockroaches and sharks and stuff like that, that doesn't count. This species, remember, the species level, has to come into existence in the fossil record, and then in the fossil record disappear in a short amount of time. Short-lived. All right? But you can't correlate it to other parts of the world unless that organism, that species, was geographically widespread. Humans are geographically widespread. Our ancestors in the fossil record came into existence as we kind of fit it somewhere to 3 to 4 million years ago. By the way, 3 to 4 million years in geologic time is short. Okay? And of course, you got to recognize it. You CSI fans and all that stuff, those new TV shows out there, is that a deer bone or is that a human bone? What is the fossil you're looking at? That's why students have to memorize all the paleontology, take all of the classes in biology to learn about bone structure and so on. Learn that biology. So remember those 3 criteria. Remember those for index fossils. That will come to you. Another little trick, excuse me, another trick wasn't just with one fossil, an index of one particular species, but multiple types, an assemblage, 3 or more very recognizable fossils, but it didn't matter how long they lived. And I got these little bar graphs in here to show you that. Let's say that in here, that from the bottom up represents time, going from older to younger towards the top, and this bar represents species A lived this long. And then species B lived this long. Species C lived the little short one on the right. Each of those lines are long in geologic time, but if you find the same 3 species in the same rock packages on a worldwide basis all the time, what do they have in common? Well, they have the rock type in common, but it's this little short span right here that they have in common. And this gets into a little more statistics and other details with that, but that's an assemblage, and that's how we use that idea. Once in a while, we have some other little key marker beds that are kind of recognizable. We have a lot of them out here in Kansas. They're altered volcanic ash. So key or marker means the same thing, a key bed or a marker bed. And these volcanic ashes that might be an inch or 2 thick get altered into a mineral mineral assemblage called bentonites. A lot of these are used in drilling industry and oil, by the way, but they're very recognizable. You go out to a Smoky Hill and they end up like a little barcode pattern, and we can just match them up really easy. If we're lucky and those bentonites have a radioactive element in them, we could actually put a number to it, which we do, by the way. All right, unconformity, another type of strange feature that we see in the rock layers that tells us, whoops, something's happened. There's a break here. Something went on. Well, what an unconformity is, it's a buried surface that was created by some erosional event in the past, destroyed some layers of rocks. Or there's a break in time, but nothing happened. There was no deposition. And there's 3 kinds of unconformities that we're going to look at. Excuse me. The first 2, disconformity and an angular unconformity, involve sedimentary rocks above or below this layer, this unconformity, this surface. Disconformity and angular unconformity involve sedimentary rocks above it and below it. The last one, if you're into definitions like nonconformist, a nonconformity, okay, is where the rocks on top are sedimentary, but the rocks on the bottom are igneous or metamorphic. So the top 2, just sedimentary rocks, the bottom sedimentary on top of the other 2 kinds, igneous and metamorphic. So what I'm going to do now is go through some little cartoon pictures that show you how these form, show you some real ones, and we'll move on to the next part of this. So disconformity, angular unconformity, which is almost like, that kind of, I can almost visualize something like that. And of course, the nonconformity. All right, here's some cartoon sequences of a disconformity. We have a lot of these in western Kansas. You get some layered rocks. A is the oldest, B, C, and D. The top part of this represents the water. Now this land gets uplifted on the left, so it's shoved up above sea level. Erosion starts to take place and destroys some layers. So it destroys all of D and a little bit of C. Now the land gets suppressed again, and you put a new layer on top, a younger package. Now if you walk out to the rock layers and look at it, you just see what appears a bunch of horizontal rock layers. Okay, that's it. But there's a gap, there was a break, there was a destruction of rock, there was a destruction of evidence. The rock layers, by the way, okay, still sedimentary. What's the relationship between the orientation of the layers above it and below it? They're parallel. That's a disconformity. That's all it is. Now they kind of highlight the unconformity as a wiggly dark line there, kind of as, related to that erosional undulatory surface by erosion. So we go out to western Kansas, Smoky Hill Chalk. You go out there and you think it's nice and continuous deposition. It's not. There are breaks in the fossil or the sedimentation record. Disconformities. All right, angular unconformity, the second one. Little cartoon on the left again. Excuse me, where's my mouse? Okay. Same story, except this time we don't just push it straight up. We crunch it. We crumple it all up with folds. So they're all tilted at different directions over here. Erode a bunch of the stuff off on the top. Push it back down below sea level and put some horizontal rocks on top. What are the rock types again? Sedimentary above, sedimentary below. But the ones below are what? At an angle. So they call it an angular unconformity. That's it. Real simple. So if you ever drive out in the northeastern part of New Mexico, Dry Cimarron Canyon, you can see the rock layers on the bottom are tilted and angled to the left. You can probably just make out that little line, or darker line right in here. Okay, and then deposited right on top, this other line is the contact of the boundary between these horizontal ones on top and the tilted ones on the bottom. That's about the best kind of angular unconformity we have closer to home here in Hays, Kansas. Turns out to be the Cretaceous Tertiary, or KT boundary, Triassic boundary. Okay, Grand Canyon. Now you're sitting there on the rim. It's pretty, it's neat. Great spot. But if you're a geologist, you start maybe thinking of other stuff. You go, oh yeah, there's some boundaries of rock types there, and way down at the bottom I've got these rocks that are 1.7 billion. There's a big gap. And when there's a big gap in here, and all of a sudden they're, between 1.7 billion and 550 million is a huge break in time. There's a big nonconformity along there. Sedimentary rocks on top, igneous or metamorphic on the bottom. Nonconformity. This is the Vishnu schist down here. It's a metamorphic rock, and then these sedimentary rocks on top. Tapeach sandstone and the Vishnu schist. Another place in it. So there's this huge break, a big great gap in time. So we've also called that one in the Grand Canyon where there's such a tremendous break, and it's not only there are others. They call it the Great Unconformity, but it's still a type of non-conformity. All right, some newer principles that came about. The principle of cross-cutting relations. And we're going to talk about two kinds of things that could cut across something to break up that layered look. One type of thing that could break it, we've already discussed, a fault. Normal faults, thrust faults, right? Now this is going to make great fodder for a question and true and false question on your test. Here's the statement. The fault or the intrusion, which would be an igneous rock kind of thing, they got these little slices here cutting in and intruding, a dike and a pluton, cutting into these other rocks, okay, cross-cutting them. So we have a fault, okay, right here. By the way, what kind of fault is that? There's the hanging wall up here, footwall here, and this yellow layer H has dropped down. That's a normal fault, okay? So the rocks have to be there before they can be cut. The layers have to be there before they can be faulted or before they can be intruded. So if they have to be there first, they're older. So the fault or the intrusion is always younger. Remember that. the fault or the intrusion is always younger. Let me ask you this. What's older? This intrusion here, which continues up to the surface, or the fault? Which is, did I say older? Which is older? The intrusion is older because it was offset or cut by the fault. Now, you don't know how many years, but you know it's a relative statement. And these are the little clues we look for. Now, here's another, and probably the last principle, I think. The principle of inclusion. Let's say you got a group of people that they've always kept you out of their group, so to speak. And now you get to move into the group. You're the new kind of, well, I don't want to use that analogy. All right, that's not good. Let's just look at the rock layers. All right, sometimes my social ones got out of hand. The inclusion is always older. Now what that means is, and I'm going to use these two cartoons on the left. The cartoon on the far left shows a granite body, a pluton that was intruded, and it started to get eroded. And rock layers were deposited on top of it. And right at the bottom of this yellowish-looking sandstone are these big boulders and cobbles. Those boulders and cobbles are called the inclusions, and they're included in the sandstone. Okay, they're in the sandstone, so they're older than the sandstone in that case. So if we look at the bottom left diagram here, we can see some of these boulders. They're weathered out of this rock on the bottom, and they're becoming included in this gravel on top of it. The inclusion is always older. The other cartoon looks very similar. We've got these sedimentary rocks there that are first. They got there and formed first, and then we get this younger granite, this magma squeezing up and pushing into it, and some of these big sandstone chunks fell down into the batholith, into the magma chamber. So these yellow rocks here, those are the inclusions. So the inclusion, again, is always older. And I've got two real examples of some older inclusion rocks in certain kinds of metamorphic and igneous conditions out in Colorado. So one was always younger, one was always older. Good, true, and false data. So they built this time scale. They came up with they were studying rock packages and quarries around the world and wherever, and said, we got to name these rocks so we can communicate with one another. So I'm going to make you learn 3 names. The etymology, not entomology, that's something else. Etymology is the study of the origin of words, okay? What's the etymology of Mississippi and Pennsylvania? They were studying rocks where? Mississippi and Pennsylvania, that's it. That's in North America, by the way. As you look at that chart again, they've got another name up there called Carboniferous. These were the coal-bearing rocks. Time period when there's a lot of coal, a lot of swamps. Potential for coal, anyway, all right, being formed. But in Europe, they call it the Carboniferous because of the carbon-rich coal. That's pretty obvious. Let's take a look at the bottom one. Cambrian. Sounds fancy, doesn't it? It's not. They were just studying some rocks in a place where they were in the British Isles, and they said, you know what? We got to make a name up for this package of rocks. And I was a historian buff, so I liked the Roman Empire. And the Romans used to call this place something. Way back when the Romans were trying to conquer the world, they called it Cambria. It wasn't called England. They called it Cambria. That's what the Romans called it. So they said, that's cute. That's kind of cool. We'll call these rocks Cambrian. That's it. Like Thursday comes from the god of Thor, a Nordic god. Where does July and August come from? 2 egotistical Roman leaders, Julius Caesar and Augustus Caesar. That's why our clock's all messed up and we got leap year and all this other stuff that goes on in there. Everybody wanted a piece of the fame, I guess, okay? For you Jurassic movie fans, Jurassic time period, the old dinosaur time period. Well, they were studying a package of rocks in Europe, the Jura Mountains. That's it. They were in the Jura, J-U-R-A, the Jura Mountains. So they came up with Jurassic. Now Cretaceous, we have a lot of Cretaceous rocks in western Kansas. The word Creta means chalk-like. So all these limestones out here are kind of chalky, soft limestones. That's it. Cretaceous. They're chalk-like. So way up here at the top in the diagram where these arrows are pointing, bottom's Cambrian, then Jurassic, then Cretaceous. Remember those, okay? Of course, you could probably think Devonian from Devonshire. The list goes on and on. So what about the numbers? See the numbers on the charts? Where'd they come from? That's absolute dating. Well, that's our next step, absolute dating. What it's based on is when we began to learn more in chemistry and physics about how certain elements break down and decay and give off atomic particles, subatomic particles. Some of this radioactivity we know is pretty nasty stuff. Okay? So it's based on radioactive decay of isotopes. You remember way back in the beginning of the course we talked about what an isotope is, same number of protons but different number of neutrons in a nucleus, right? You don't need to remember that, but just remember this radioactive decay bit. Now, the decay, when an atom gives off these particular particles, not everything is radioactive, by the way, only certain elements are. And when they do break down, they do it in different ways. But we can measure it. Every particular radioactive isotope has its own specific decay rate and constant, and we can measure it. And they're not all the same. If I pose a question to you on the test about all radioactive elements decay at the same rate, that's false. Some take a long time to break down, and some are much quicker, much shorter than that. But each one has a very constant and very measurable, and that's the key thing, and it doesn't change. It's one of those laws in physics that we can measure and they don't change. That's the key thing. Here's an example which you can just look at. You don't have to write anything down or know anything about this diagram. Okay, about rubidium breaking down to strontium. Rubidium's a radioactive thing and it can give off certain particles. That's what the diagram's kind of showing. Now this one gives off a certain kind of particle, but they can give off different kinds of particles. If you had your chemistry or physics, you know what these are, the alpha, beta, or gamma particles. Different styles of how an atom will break down. And sometimes it just doesn't, boom, break down in one step. It might take multiple steps to get to its stable product in the end, like uranium down to lead. Now, one of the things that we do kind of push across is the idea of half-life. Each of these different atoms have a different radioactive half-life. And it's defined as the time required for 1/2 of the original radioactive substance to break down or decay to a stable atom. Now in the literature they call it a parent atom for the unstable radioactive one, and for some reason they call the stable product the daughter. Guess you sons are out of this loop. Meaning I guess all parents are unstable. Sometimes I thought I was. Go a little bonkers about things. We only have one. I can imagine having 12. Okay? So if you take the original amount of material up here in this chart, up here in the top left, 1 unit of radioactive stuff, and 1 half-life goes by, it breaks down to 1/2, 50%. So what do you have? You have 50% stable, 50% radioactive. So the radioactive stuff's still going to break down. So 1/2 of 1/2 is what? 1/4, and then 1/8, 1/16, and so on. And theoretically, you never get to 0. But it plots in this kind of a curve, hyperbolic curve on there, okay? Now, we've been able to measure and calculate these half-lives for a whole bunch of things. Well, what are we dating? What's being dated in terms of the geologic stuff? Well, one is, if it's an igneous rock being dated, we make the statement that we're dating the time of when it got hard, when it crystallized. That's when the clocks start in our book. So we're measuring the time of crystallization of that magma. So if it involves a mountain or a volcano, we could put a number to it. If it's in a sedimentary condition, a little bit more difficult situation, but we're measuring time of deposition, when that rock begins to be, the layers are being compressed and eventually hardened into a rock. So when did it get deposited? If you're working with metamorphic rocks, it gets a little more complicated because it's pressure, but mostly temperature. The temperature can kind of reset the clock sometimes. So we do all of them, try to come up with a uniform statistical approach to say, yes, this is coming up with about the same date. So time of metamorphism. So we cover all 3 rock categories. Now, don't write any of this down yet. Just look at it. Here are some common ones. Uranium breaks down to lead, potassium to argon, rubidium to strontium, carbon to nitrogen. Each of you in this room have radioactive carbon-14 in you, in your bones and your teeth. Now, it's not that bad stuff, though. But when you die, you're not going to get any more brought into your bones or your teeth. It's in the atmosphere. You breathe it. Carbon-14 is part of carbon in the atmosphere. And so you're not putting it in. So once that stops, then the clock's going to change, the amount of product in there. So things that are living will have a lot of that, anything with carbon in it. Okay, so what I would like you to kind of remember would be a few other things that are towards the bottom of the diagram. That in the sedimentary rocks, there's a weird little green mineral called glauconite. Glauconite is used in sedimentary age dating, and it's got radioactive potassium in it. Some of those potassium atoms are radioactive. So glauconite was sedimentary rocks. Weird minerals, now you know about the micas, biotite and muscovite, we covered those earlier. I don't know if I mentioned zircon, another strange zirconium silicate, which used to crush up and put in toothpaste, by the way, years ago. Those you tend to find in igneous and metamorphic rocks. And then rubidium and uranium, and sometimes potassium, you find those in there as well. So these minerals with igneous and metamorphic, and then glauconite. Now if you're an archaeologist or anthropologist, bones, wood fragments, shells, calcium carbonate in their shells, the carbon in there, even in some ice where carbon can get trapped or in water, we can age date things. But the half-life for carbon-14 is really small. So geologists don't use carbon-14 dates as much as an archaeologist or anthropologist would. Here's a new one, taking pictures. When did the camera get invented? When did people truck all around the world and take pictures of things? Well, here's a picture out west, okay, 1871. Attempt to put the camera back in the same place and see if it's changed about 100 years later. So we do some photo comparisons. Here's out here in western Kansas, Castle Rock in Gove County. 1867 photo. That's a long time ago. There it is in 1997. What's happened to it? It's fallen apart. It's eroding and breaking down, the landscape. So we could do some general timing rate of stuff with that. So not too long ago, just 5 years ago, big chunk, this whole thing, see how it's starting to look like it's almost tilting? That fell off. Cobra Rock, a famous one out there, fell off too. Okay? So people are, that thing fell down. Nobody was there at the time it happened, fortunately. So now we get fancier. Remember I always talk about new toys we have, with stuff, satellite data. I mentioned this the other time briefly about magnetostratigraphy. We go out there and take that special saw, we core the rock out, mark it in terms of its orientation, and we bring this expensive little sample back, a little instrument to cut this up at about $35,000, and then the instrument to measure the age date's even more expensive. And so we will measure then the magnetic character, the polarity reversals within those rock layers. And once we get that, here we see a little chart on the bottom right of this diagram that here's one particular direction of the magnetic field, and then bam, it changes in this, right in a short period of time. Well, that's a reversal that happened, and we put it in this chart. Remember I said it looks like a bar graph. So if you can go find some rock layers and you get the dates and you create your bar graph, you just move your bar graph up along the side of this and see where they line up. So that's gotten better and better and better as we collect more and more data. So magnetostratigraphy, a fancy way. Now, we got a lot of others. I'm going to show you a list. I'll go through the list kind of quickly here of some really bizarre stuff that we use to kind of figure out time. That's what this is all about, time. How old is something? And some of these are relative and some are absolute. Dendrochronology. Who's a biology major in here? Who wants to admit one? What is dendrochronology? Dr. Thomason may take you out and make you do this. I'll show you what it is in just a bit. Okay? Fission tracks, really wild, goofy thing. Lichen growth. Looking at the diameter of these lichen patterns that grow on the surfaces of rocks. Coral growth rings. The Earth is slowing down in its spin because it's been collecting more mass. So the length of day was a lot shorter in the geologic past, so the growth rings will vary, how we see this kind of stuff. Hydrated obsidian, a really bizarre one that archaeologists use. So there's a lot of chemistry, certainly a lot of physics, and some mathematics involved in this, particularly statistics. And there's many more, and the list goes on, but let's look at some of these, okay? Dendrochronology, and I'll come back to most of these. I think I got pictures of them, except coral growth rings. I don't think I threw a picture of that in. Dendrochronology is a study of tree rings. There's the growth patterns. Doesn't that look like a barcode again? Sure. Wetter years, you got a bigger band. Drier years, it's narrower. There was a fire went through, you get a scar. And we can then take these cores out of these trees and overlap and find the overlapping patterns and go further and further and further back in time. Really cool. Fission tracking. Remember the atom decays and breaks down, those little particles, gamma and alpha particles go blasting out? Well, they can go through the crystal and, like the movie The Core, and they're drilling down to the core and they're moving rocks around, creating their path line. Well, that's what can happen in the mineral. Under a microscope, you can see these little pathways where those radioactive particles that are blasting out from the nucleus are leaving, or wherever they're going, what part of the atom they're coming from. So we measure the length of that line. That tells us time. Lichenometry, the lichen diameters, how big the patch is, and go back and measure them over years. A lot of interesting, weird work with that. It's just algal stuff on the surfaces. Obsidian, hydration. Arrowheads. When was it made? If it was underground, how long did it begin to oxidize or chemically alter? And what they do is they go under a microscope and they look at the very thin, sharp edge of that and calculate how far chemical erosion has eaten into the thin edge of that particular, say, spearhead or arrowhead. What does Cretaceous come from? What's Creta mean? Chalk-like, okay. Jurassic from the Jura Mountains. And Cambrian, where'd that come up from? Got the Roman name for Cambria, that's the etymology of it. So we're almost done. We're getting close to some numbers and we'll be done today, okay? How old then? What are the numbers? Well, the oldest rocks that we're finding today are either in Australia or Canada, and the Australians and Canadians have a contest going. They're always, well, our rock's older than your rock's, kind of, your grandmother wears army boots, old stories like that. And they're always in the literature fighting of who's got the oldest rock. Now for this class, we're going to round them off in between. But you don't need to remember 3.96 or what those rocks are, like metamorphosed granites or sandstones. You need to remember, though, that the oldest, and this is the most important part of this, the oldest dated rocks are around 4 billion with a B. 4 billion, not million with an M. 4 billion years old. I put the 4.1 billion in quotes because they're still arguing over that a lot. But this has been dated many, many times and confirmed a lot. Some old stuff. Oldest rocks are 4 billion years old. But yet on the diagram we say, hey, we think the Earth is 4.6 billion. Well, where do we come up with that? The oldest rocks are 4. So where's that other 600 million? Well, we haven't, studied all the rocks yet, and a lot of rocks have been destroyed. Okay? So they've either been eroded or they're covered up. So we might find them in our research and our explorations of things. Still doesn't tell us much, though. Well, we've gone to the moon. Another one of our solar system buddies. We're making an assumption it formed about the same time as Earth did, close to it. Samples brought back that age dated 4.4 billion years old. So that gets us a little bit older. How come we didn't find 4.6 on the moon? Well, we haven't been there a lot. Haven't dug all over like we have the Earth, so maybe someday. But other celestial solar system related material that comes here for us in the form of meteorites. The oldest dated meteorites are 4.6 billion, so that's where it comes from. That's it. Now there are some other mathematical gimmicks we can do with the with those radioactive decay things. We can try to project backwards from a sample by trying to set the clocks back to 0. And that's a little, again, more modeling and geochemical things that we can do. It's kind of complex. So Anybody have any questions on this material that I've covered today before we end? Okay, that's it. We'll see you next week, and I'll send you an email about the exam 4.